In this video, we're going over a lot of definitions related to random variables and discrete probability distributions, and how you can calculate different facts about those distributions as you go. So first, let's talk about some of those words that I've already used and what they mean. A random variable, usually written as x, describes the possible outcomes from a random experiment. So it's the list of things that you're seeing come out of an experiment. For example, if we were tossing a coin, the random variable could take on the values of tails or heads. Discrete means the values that this variable can take on are distinct from one another. So we could think of this as the integers 1, 2, 3, or separate outcomes like heads or tails. You can't have something that's in between these values. Continuous would mean that it could take on any value within an interval. So it could be something like height, where you could vary by fractions of an inch, and you can see a variety of values coming out of this experiment on this interval. A probability distribution, by definition, describes the probability that a random variable takes on a certain value. So in this case, we're talking about the probability of those discrete or continuous values occurring. There are a couple of facts that you want to check to see if a probability distribution is valid. Each individual probability has to be between 0 and 1. Remember, probability as a decimal represents a percentage chance of happening, and you can't have more than 100% chance. The sum of all of the probabilities, so the probability of each of those different values that it can take on, must add up to 1. Because again, you can't have more than a 100% chance of something happening. There are also a couple of ways that we can demonstrate probability distributions. We'll talk about functions later on, but visually you can make a table or a graph where it displays the values that the variable can take on. So this one is a discrete random variable, and you can also display the probability of each of those variables happening. Once we have a probability distribution model established, we can find the mode and the median of that model. Just like when we're talking about numbers and sets of numbers, the mode is the most frequently occurring value. In this case, that aligns with the largest probability, and the median is the halfway point or the 50th percentile. So it's the moment when all of the probabilities have added up to 50%. One way you can think of this is like a frequency table. In fact, you can think of this like a frequency table by multiplying by 100 on the probability row and thinking of it as an experiment that had 100 entries. This might help you to understand the mode and the median a little bit better, because then you can consider that there might have been 50 entries by the time you've gotten to that 50th percentile. This is an example of doing that. I can now see that the most frequent number that popped up in our experiment was 1, and that we would have 50 results by the time we got to a result of 1 if I listed all of the different results in order. So I would have a list of 25 zeros and 50 ones and 25 twos, and the 50th number would be a 1. Here's an example of a problem that we can try out making our frequency table and finding the mode and the median. So we have a store that sold gum and recorded the number of packs each person purchased in 1 week. 13% purchased 1 pack, 42% purchased 2, 15% purchased 3, and 30% purchased 4. So the first thing we want to do is establish all the values that x can take on. So x can be either 1, 2, 3, or 4. I assume that they didn't record somebody if they didn't purchase gum. Then let's make a probability distribution table. This is the most frequent way that we will see these distributions written out. So we want one row for the values that x can take on, and then we want one row for the probability that x took on that value. Our different values for x were 1 through 4, and the probabilities we'll take from the word problem, but write each percentage as a decimal point, since we're writing the probabilities. So 1 pack is 13%, 2 packs 42, 3 was 15, and 30 for 4. To find the mode, we want to look for which number popped up the most number of times. And if you consider that these percentages are a proportion of the actual experiment, then the one with the highest probability is the one that showed up most frequently. So the mode number of packs of gum would be 2 packs. The median would be the value that we get to when our probability has accumulated 50%. Or like I said earlier, if you want to think of it like a frequency table, you can think of a list which has 13 ones and 42 twos and 15 threes, and you're writing out that whole list of 100 different outcomes. Which one would be at the halfway point, which is the 50th term? So I would have a cumulated 50% somewhere in this area on the table. If I go all the way to the end of 2, I'm definitely above 50%. So I know that these last two numbers are definitely not at that 50% mark. And 1 is too small to be 50%. So I know since it's going to fall somewhere in here in the range value of 2, then 2 is also going to be the median. I hinted earlier that we're going to talk about functions to describe the probability models, and that's our next vocabulary word. We have a probability mass function. It is a function whose domain is the possible values of x and whose range is the probability distribution. Let's take a look at what these can look like. So here's a probability mass function. Note that we have to give you the domain for this in order to plug those values in and not get probabilities that are outside the scope of the experiment. So this is an experiment that had 4 values or 4 possible outcomes, and using this probability mass function, we can find the probability that x took on each of these values. So for example, if I wanted to find the probability that x took on the value of 2, I'll just take the probability mass function and plug in 2. Notice that that fits the requirement for a probability, which is that it is between 0 and 1. It is neither negative or greater than 100% chance. To test if a model is valid, you want to check that all the probabilities for each of these values adds up to a total of 1. Here's an example of that work. I found the probability for each of the different outcomes, and they all added up to 34 out of 34, which is 100%. So this is a valid probability mass function. Last topic is expected value. The expected value is the mean of the probability distribution. It's the average value of x as the experiment is repeated. So basically, what kind of value do we expect to come out of the experiment more often than others? Let's take a look at that gum example that we just did and see if we can find the expected value for that situation. To find the expected value, you'll take the value that can come out of the experiment and multiply by the probability that x takes on that value, and do that for each of the different terms and add them together. So it's going to be the sum of the product of each column in the table. So for this one, we would do 1 times the probability of 1, 2 times the probability of 2, 3 times the probability of 3, and so on. And because we're multiplying them, what we would expect is that the mode is going to be close to that average because it showed up the most, so it basically has a higher weight in this multiplication, and our expected value should be close to that. I used a calculator to do this calculation quickly and got 2.62, which is exactly as I said, close to the mode value. This is considered the average, the mean, or the expected value of this experiment. So we expect that most people will carry 2 to 3 packs of gum. A fair game is a question that can follow from an expected value. A game is considered fair if the expected gain is 0. So that doesn't mean that you will always walk away with no gain. It means on average, you will walk away with no gain. So the chances of you walking away losing and the chances of you walking away gaining are balanced. To find your expected gain, you want to consider what the expected outcome is. minus the amount that you put in. Usually this is money or tickets that you put in and you get out. Here's an example of a game. Let's say that you can spin a spinner and you win a certain amount of money based on what pops up on the spinner. It costs $5 to play the game, so we want to know what the expected gain is if you decide to play. The game would only be considered fair if the expected gain is 0, and it would be in your favor if the expected gain is more than 0. But you are more likely to lose money if the expected gain is less than 0. To find the expected gain, we first need to find the expected outcome from this experiment. If this is a fair spinner, then the probability of each of these winnings is exactly 1/4. To find the expected value, we'll multiply the outcome with the probability of you getting that outcome. The expected outcome is $4. Now, of course, we can see that $4 is not actually an amount that you can earn. It is the average amount that somebody would earn if they repeated this experiment multiple times. So your gain, in this case, is 4 minus the $5 that you put into the game, which means you're expected to lose $1. So because this expected gain is not 0, then this game is not considered fair. And in fact, because it is negative, this is a game where you're expected to lose money on average every single spin. Okay, that is everything I've got for you. Hopefully this was a good introduction to the concept of a probability distribution model. There are many different types of specific models that take on specific patterns, but overall these concepts are what we use across the board in statistics. Thanks.